Well, dear friends, this module onward, we are going to study the theoretical aspect of electrodynamics, that is studying physics part of electrodynamics. Studying physics part means to try to get the answers of the questions what, how, when, etc. The great mathematician and physicist Clerk Maxwell, he has done a lot of work in the respect of electromagnetic fields. We should not iterate the fact that in electrodynamics we mainly study the electromagnetic fields and the related phenomena. Once I asked the question in the class, dear student friends, what is meant by electric charge? One of the students answered that, sir, electric charge is that something which produces electric field. The answer was noteworthy. I started thinking that can we not generalize this statement saying that charge is that entity which gives rise to force field. Accordingly, we can have gravitational charge giving rise to gravitational field, thermal charge giving rise to thermal force field, magnetic charge giving rise to magnetic force field, so on and so forth. Maxwell, with the help of his 4 differential equations and the equation of continuity, could explain practically every phenomena in the field of electrodynamics. The equations are quite marvelous. We are going to study some of the important aspects regarding these Maxwell's equations and the properties of the medium in which the electromagnetic fields they are moving or they are interacting with each other. It is not possible to cover all the aspects of Maxwell's equation in such a short duration of the lecture, but we will try to cover up only some important points regarding Maxwell's equations. This module will help you in understanding Maxwell's equations and their association with various laws of electromagnetics. It will also help you to know about electromagnetic properties of media. It will be useful to understand the deduction of laws of electromagnetics from Maxwell's equation. Also, in addition, it will be useful to understand the concept of displacement current density as Maxwell's contribution to electrodynamics. Before we proceed to discuss about the laws of electromagnetics, let us express our deep sense of gratitude towards the eminent physicists for their remarkable contribution in the field of electrodynamics. At the introductory stage, instead of using mathematical rigor, simple consideration of dictionary meanings, analogies, plain and independent thinking may be useful in understanding roughly the meaning of any term or concept in science. With this view, let us try to understand what is meant by field. Now think over the answer. Field is a region of space at every point of which we can associate a physical quantity. If the physical quantity is scalar, the field is called as scalar field. Vector physical quantity, on the other hand, will correspond to a vector field. The field is named after that physical quantity. Thus, we can have temperature field, pressure field, density field as the examples of scalar fields, while velocity field, force field, etc. are the examples of vector fields. Then what is a force field? Force field is a region of space at every point of which we can associate a physical quantity force. That something which gives rise to the force is called as corresponding charge. Thus, accordingly, we can have a pair of gravitational force field and the gravitational charge. On similar lines, we can think of electric force field and electronic charge, or magnetic force field and the magnetic charge. Can we think of a magnetic charge? Can a current carrying element be thought of being the magnetic charge? An electronic charge in motion is equivalent to a current carrying element. Answer to such questions regarding magnetic field are not so simple. It needs deep and careful thinking. Maxwell's equations relate electromagnetic force fields and the corresponding charge densities. Various laws of electromagnetics were established by eminent physicists long before Maxwell. Some of the laws are as listed here. Coulomb's law is one of the simplest but very fundamental law of electromagnetics. Maxwell's equations and their association with different laws of electromagnetics are as shown. Note the occurrence of divergence and curl of vector fields E, H, B and D in these equations. With the help of mathematical theorems discussed in the earlier modules, we can express Maxwell's equations in integral form as shown. Note that one has to deal with line integrals and surface integrals. The physical quantities represented by different letters in Maxwell's equations are as shown. E and H represent the intensity of electric and magnetic field and are defined as force per unit charge. B is magnetic induction representing magnetic lines of force per unit area. D is the electric displacement. Note that B and D are similar physical quantities. The electric field E at a point can also be measured in terms of electric lines of force crossing normally per unit area. The total number of electric lines of force passing through a given area is termed as electric flux d phi and is given by d phi is equal to E bar dot ds bar. In general, flux of any vector A bar through an area element ds bar is given by the dot product A bar dot ds bar. We can have magnetic flux, luminous flux, neutron flux, etc. In Maxwell's equations, we deal with force fields. Several questions may arise in our mind regarding their generation, range, role played by medium in their generation, limitations if any, and many others. To get the answers of these and some other questions, let us discuss Maxwell's concept of force field rather qualitatively. It will be interesting to go through the historical and theoretical discussion made by Maxwell and many of the then physicists regarding this concept. However, we will try to understand this concept in a simplified manner. We have discussed some aspects about force fields in the beginning, but the main question is how the force field is set up. Maxwell, in his field theory, has given the concept of electric force field, which can be briefly summarized in the form of two statements. Statement number 1. If we place an electric charge at a point, it modifies the properties of the space surrounding it and produces its own field in the space surrounding it. Statement number 2. If we place a test charge from outside at any point in that region, the test charge experiences a force. Please note that the concept of force field consists of two parts. In the first part, the establishment of force field due to the charge is stated, while the second part deals with testing the existence of force field. There are many points to be noted in this concept. Firstly, the field is set up instantaneously. Secondly, it is understood that the charge modifies the properties of the space surrounding it while setting up its own field. Thus, the properties of the medium or space are also involved. The space or medium have many types of properties such as thermal, electrical, magnetic, gravitational, etc. Out of these, which property is modified by the charge? The answer is simple. Only those properties are modified corresponding to the nature of the charge. Gravitational charge will modify only the gravitational properties of the medium. Similarly, electric or magnetic charge will modify only electrical or magnetic properties of the medium respectively. They will not change the gravitational or any other properties of the space or medium. Here we note that the electric charge will try to modify the properties of the medium, and medium also allows to permit to change its properties. How to measure this property of the medium? For this, we define a physical quantity called as electric permittivity of the medium. It is denoted by epsilon and may be defined as the extent to which the medium permits to change its electrical properties due to the presence of electric charge is called as electric permittivity of the medium. Similarly, in the case of magnetic charge, we can think of magnetic permittivity. However, due to the elastic nature of magnetic field, we use the term magnetic permeability instead of magnetic permittivity. It is represented symbolically using a letter mu. Thus, the extent to which the medium allows to change its magnetic properties due to the presence of magnetic charge is called as magnetic permeability of that medium. On which factors do the permittivity and permeability depend upon? Definitely, they depend upon the medium. For different media, permittivity or permeability can be different. For a given medium, does permittivity depend upon the charge? Can any increase in the strength of the charge cause increase or decrease in the permittivity of the medium? Does it change with temperature? Just think over these questions. It is a big issue having theoretical importance in physics. Analogical examples always help in understanding the concept in physics. To understand the concept of force field, let us consider an analogical example. Listen, think and decide to what extent it can be useful. Let us consider the atmosphere in the classroom before the teacher enters the class. How is it? It is very good, joyful, isn't it? Well friends, let us consider an analogical example of the students waiting for a lecturer for the lecture in a classroom. Before the lecturer comes or before the teacher comes, what is the atmosphere in the class? Very joyful. Students are going here and there, they are discussing with each other, they are peeping out of the window, etc. Very beautiful atmosphere. What happens when the teacher comes? As soon as the teacher enters the class, all these activities of the student, they stop and everybody is attentive to the teacher. What teacher has done? Merely because of his presence, he has produced his own field in the class. Now, if a student is late, the latecomer student will have to ask the question, may I come in, sir? Why? Because that student understands that the teacher is present, his field is there, and that's why we cannot enter unless we take his permission. This simple example can be useful for understanding the two statements. Teacher, you treat it as a charge. The students in the class as medium. And changing the behavior of the students, that is, they are attentive to the teacher, that modification in the atmosphere, that is nothing but modification in the property of the space by the charge. The student who is late and who wants to come in from outside, he may be treated as a test charge. I hope that if you think over this example, you will understand the concept of force field. Assume the students in the classroom as medium. The analogy can be extended further to discuss about the nature and the property of the medium, range of force field, etc. Such analogies, though not 100% accurate, can be useful in understanding the concepts in physics. What are different types of media? In electromagnetics, we talk about different types of media such as free space, dielectric, conductor, insulator, semiconductor, etc. We use the term isotropic, linear, homogeneous, inhomogeneous, etc. as regards the nature of the media. We define various types of physical quantities to account for various types of properties like permittivity, permeability, susceptibility, polarizability, conductivity, mobility, etc. Let us try to understand the meanings of some of them. What is meant by free space? In electromagnetics, it is assumed to be a space which is free of electromagnetic and gravitational force fields. Can we really have free space? The answer is no. However, for all practical purposes, vacuum may be taken as a free space. The electric permittivity of a medium is denoted by epsilon, and the electric permittivity of free space is denoted symbolically by epsilon naught or epsilon 0, whose value is 8.85 into 10 raised to minus 12 farad per meter. The magnetic permeability of a medium is denoted by mu. The magnetic permeability of a free space is symbolically represented by mu naught or mu 0 and has a value mu 0 is equal to 4 pi into 10 raised to minus 7 Weber per meter. Iron, nickel, cobalt are examples of magnetic materials. Dielectric material. It is a material having property of transmitting electric force from one point to another without conduction through it. Glass, wood, paper, air, mica are some of the examples of dielectric materials. The ability of the dielectric to transmit the electric force through it without conduction is measured in terms of its dielectric constant K, which is defined as shown and is a dimensionless quantity. Dielectric constants of some materials are as shown in the table. Conductors, insulators and semiconductors are the terms most familiar to all of us. The term can be better understood in terms of a quantity known as energy gap EG, measured in electron volt. However, we will not discuss about it here. In the presence of a dielectric near a given charge distribution, the initial electric field at a point is altered. Rather, it is reduced in magnitude. It is because of a phenomena known as electric polarization. The atoms and molecules in a dielectric may undergo a change in the relative positions of the centers of positive and negative charges in them due to the application of external electric field. This in turn can give rise to a net electric dipole moment in the dielectric. Due to this, the dielectric exhibits electrical properties and we say that the dielectric is polarized. Electric polarization at a point is defined as electric dipole moment per unit volume and is denoted by P bar. SI units of P are coulomb per square meter. The three vectors D, P and E are related through the relation D equal to epsilon 0 E plus P, where D is called as electric displacement vector. The electric dipole moment per unit volume is taken to measure the average polarization. Note that the field due to polarization is always opposite to the externally applied electric field. Hence, in general, it is said that the presence of a dielectric reduces the externally applied electric field due to polarization. The vector P represents the polarization at a point and has units coulomb per square meter. The most difficult topic in electrodynamics is the magnetic materials and the process of magnetization. It is very difficult to give proper justice to it in a short duration of the lecture. However, let us try to know about only one important quantity known as susceptibility. An electron moving in a closed orbit around the nucleus in the atom is characterized by magnetic moment. When external magnetic field is applied to a magnetic material, the relative orientations of the electron orbits in different atoms may change, giving rise to a net magnetic moment in the material. Due to this, the material exhibits magnetic properties. We say that the material is magnetized. The electrons in atoms and molecules in a given material may give rise to net magnetic dipole moment when placed in external magnetic field. If the net dipole moment in the material is non-zero, then the material will exhibit magnetic properties. We say that the material is magnetized. The magnetization due to the application of external magnetic field can be measured with the help of a vector m defined as net magnetic dipole moment per unit volume and is called as magnetization. Besides the applied magnetic field, the magnetization will depend upon the nature of the material. It is given by m is equal to mu 0 h into chi m, where chi m is magnetic susceptibility of the material. SI unit of m are same as the magnetic induction B. Magnetic induction B, the applied magnetic field H and the magnetization m are related as B is equal to mu 0 h plus m. Magnetic susceptibility is defined as the extent to which the material can be magnetized due to the application of an external magnetic field H. Magnetic susceptibility can be positive, negative or 0. The magnitudes also can be very low, medium or very high and may vary with temperature or the process used for material fabrication. Accordingly, we have different types of magnetisms and magnetic materials, namely diamagnetic, paramagnetic, ferromagnetic, antiferromagnetic, etc. The third type of material, known as ferromagnetic material, has been of much more importance due to its practical applications. The magnetic susceptibility is positive and have remarkably large value and can be increased further by adopting fabrication process. The main characteristic features of ferromagnetic materials are spontaneous magnetization, saturation limit of magnetization, Curie temperature and hysteresis. Ferromagnetic materials are characterized by phenomena known as hysteresis. When sinusoidally time varying field is applied to the material, the variation of B with H gives a closed loop as shown. The ferromagnetic materials are very sensitive to temperature. One point to be remembered is that electrical susceptibility chi E is always positive, while magnetic susceptibility can be positive or negative. So far, we have discussed about some electromagnetic properties of materials. Now, let us discuss about some peculiar features of some of the laws of electromagnetics. The first concrete step in the study of properties of electric charge was Coulomb's law. With the help of experimental observations made using a torsion balance, Coulomb put forth his first law in electrostatics. Statement of the law is as shown and is well known to us. For a system of 2-point charges Q1 and Q2 kept in free space with separation R, the force can be expressed mathematically as shown. Following points be remembered in connection with Coulomb's law. Coulomb's law applies to point charges only. Coulomb force is a long range force. It obeys the principle of superposition. What is a point charge? We know that a point has existence but no measurable dimensions. Can we think of a charged entity satisfying this condition? Definitely not. However, if the dimensions of objects on which electric charges are present are very small as compared to the separation between the objects, then the charge distributions may be treated as point charges. If there are n number of point charges, say Q1, Q2, Q3, etc. up to Qn, then the net force acting on a charge Q is given by the vector sum of the forces F1, F2, F3, etc. up to Fn on Q due to the individual charges. This is nothing but principle of superposition. Each law of electromagnetics has some peculiar features of its own. It will be worth noting to have a look at them. As stated earlier, we can derive the laws of electromagnetics using Maxwell's equations. As an example, let us see how Coulomb's law can be derived from Maxwell's equations, namely del dot D equal to rho. Integration over volume V followed by the use of Gauss divergence theorem yields the result integral D dot ds over the closed surface S is equal to Q1. With D equal to epsilon 0 E, we get epsilon 0 into integral E dot ds over the closed surface S is equal to Q1. Then selecting Gaussian surface S in the form of a sphere of radius r, we get the expression for E bar as shown. E bar at r bar is equal to Q1 upon 4 pi epsilon 0 r square. Hence, the force on point charge Q2 due to Q1 is given by F is equal to Q2 into E, that is Q2 Q1 upon 4 pi epsilon 0 r square. By using Maxwell's equation del cross E is equal to minus dabba B by dabba T, we can derive Faraday's law of electromagnetic induction, namely E equal to minus d phi by dt. The mathematical operations include use of surface integral followed by the application of Stokes' theorem and the definition of electromotive force. From Maxwell's equation del dot B equal to 0, we understand that at any point the net magnetic flux per unit volume is 0. The magnetic lines of force are assumed to be originating from some magnetic pole. Hence, zero divergence implies the fact that magnetic monopole does not exist. For every north pole, there is equal and opposite south pole. The significant contribution by Maxwell is the modification in the old form of Ampere's law with an addition of the term dabba d bar by dabba t known as displacement current. Ampere's law in its old form can be written in differential form as del cross H is equal to J, where J is the true current density. It can be shown that the law is applicable only for time independent charge densities. In simple words, Ampere's law in this form can be used only for stationary currents. It cannot be used for time varying currents. Maxwell modified the concept of current density as J is equal to J true plus Jd, where J true is the conventional current density wherein the electrical charges physically move. Using the new definition of current density, Maxwell obtained Jd is equal to dabba d by dabba t. With this term, he obtained del cross H is equal to J true plus dabba d by dabba t, which could explain the fields of time dependent as well as time independent current densities. Note that the electric displacement vector D can describe the electric field at a point independent of the medium parameter permittivity. Maxwell's equations have been the topic of theoretical interest for many of the physicists. Some of the questions raised in connection with these equations are worth noting. Question number 1, are Maxwell's equations really general or do they have some limitations? Question number 2, can these equations be applicable for very high frequency fields and nanosystems? Question number 3, can these equations be applied to discuss the motion of electrons in an atom? Question number 4, can the conclusion about non-existence of magnetic monopole be wrong in the field of particle physics? It will be very interesting to read about such things and the critics thereon, which give a new dimension to the process of studying science. Friends, it is very difficult to discuss about Maxwell's equations from all corners in a single lecture. We have tried to discuss about Maxwell's equations as a brief introduction, avoiding mathematical complexities there in it. So, study Maxwell's equations further in much more detail. To summarize, we can say that Maxwell's equations relate electromagnetic fields with the corresponding charge densities. By using mathematical theorems, we can derive all electromagnetic laws with the help of Maxwell's 4 equations and the equation of continuity. Maxwell's equations can be used to explain all the phenomena in the field of electrodynamics. The effects of polarization and magnetization can affect the magnitude of the external applied electric or magnetic fields. The major contribution of Maxwell is the displacement current density, which is useful for modifying the old Ampere's law. With this modification, Maxwell could explain all the effects related with time independent and time dependent current densities. Thank you.